Hello everyone and welcome to another video. Today we're going to wrap up our discussion on introductory wind tunnel testing. If you've been following along, you know that this is actually a three-part series of videos. In the first two videos we discussed the data acquisition and data reduction process. Today we're going to finish the last part of this discussion by covering data analysis. In other words, how should we interpret data coming out of a wind tunnel and what should you expect? We'll also talk about some of the things you may want to consider when planning or designing a wind tunnel test. Now, obviously, we're going to build on what we discussed in these previous two videos. So, if you haven't watched these, please take a moment right now to go back and view these before proceeding with the video today. You can get to either of these previous videos by clicking on the card in the upper right of your screen. All right, so enough stalling, and by the end of this video, you're going to understand why that is a hilarious pun joke. But with that, let's go ahead and jump in and get started. All right, so really what we want to do is after we've gone ahead and acquired all the data, reduced all the data, now we probably want to plot and look at the data, and we should ask ourselves, what should this data look like, right? What are we expecting to see coming out of the wind tunnel? So just to refresh your memory, right, remember that the two of the key parameters that we're going to be looking at now are how do the forces and moments change as a function of angle of attack alpha, and again, alpha was defined to be positive when the wind was hitting the underside of the aircraft. So again, if you think about this picture like this, if the aircraft center of mass is moving in this direction where I've expressed as VA, right, you can also think of that alternatively as the wind blowing at the aircraft in the exactly opposite direction, which is what's happening in the wind tunnel, right? So again, this picture is basically showing you a positive angle of attack where the wind is hitting the bottom side of the aircraft, right? Similarly, the other major parameter that we're going to be looking at is how do the forces and moments change as the angle of side slip increases or decreases. So again, that angle was called beta, right? And a positive beta was when the wind hits the right side of the aircraft as drawn in this picture here, right? Again, the only thing to maybe keep in mind and just be a little bit careful is some wind tunnels like to use the angle psi, which is just negative beta, right? So just something to think about. So again, we'll think about these two pictures as we move forward, okay? So a couple other things that maybe we will make an assumption on is let's go ahead and assume that the aircraft, I'm just going to abbreviate that as AC, is symmetric about the body XZ plane. So again, just to refresh your memory, right? So the XZ plane basically splits the aircraft right down this sort of center line. So basically we're saying the left side of the aircraft is pretty much the same thing as the right side of the aircraft, right? And again, that makes sense if you take an aircraft and you look at it straight down, right? I think most people would agree that the left side of the aircraft is probably the same, sorry, I was pointing to the right side. This is the right side of the aircraft, is probably the same thing as the left side of the aircraft, right? And again, you can probably see that also if we just look at this from a top view, right? Most aircraft are symmetric about that center line, okay? So that's one thing that is a good assumption to make. And for now, also the pursuant following discussion, so let's go ahead and say the rest of the discussion has data, basically our forces and moments in the wind frame. Right? And again, if you need a refresher on what the difference between the wind frame, stability frame, and the body frame is, we covered that in one of our previous videos, as you can see over here. Okay? Okay, all right. So again, I think it's easy. I like to think about things in the wind frame because I think that's as close to the wind tunnel frame. Again, we talked about the slight differences between the tunnel frame and the wind frame last lecture. That was those deals with the angularity corrections and the crossflow corrections. But anyway, long story short, the wind frame is basically what the wind tunnel is going to report to us directly, and I find that sort of the easiest way to think about it. Of course, if you're in a different application, like you're a simulation engineer or something like that, you might want these data in the body frame or the stability frame. But again, just keep in mind, right? There are multiple aerodynamic frames that we could be talking about. I want to talk about the wind frame for the rest of this discussion. Okay? All right. So with that being said, let's go ahead and ask ourselves, how do the forces, the aerodynamic forces, right, and the aerodynamic moments, how do those behave, and how are they a function of things like angle of attack, angle of side slip? We know they're also a function of tons of other things, right? Like the control surface deflections, right? Delta aileron, delta rudder, etc., etc. It could also be a function of dynamic pressure, Mach number, right? There could be all sorts of things, right? P, Q, R, right? There's all of these dependencies. The aerodynamic forces and moments all depend on all of these different parameters, right? We don't have time to discuss how these things depend on all of these different parameters. Instead, what we want to do is let's focus in on a couple of these quote-unquote critical ones. Like we said, angle of attack is probably important. Angle of side slip is important. And actually, why don't we talk about control surfaces? Maybe let's lump in all these, and maybe we'll try to sort of talk about how these forces and moments should vary as you deflect some of these control surfaces. And these are, again, we talked about this in our data acquisition discussion. It's probably very difficult to obtain some of these. I mean, I guess you can look at a dependence on Q. That's very easy to do in the wind tunnel, and maybe Mach number if you go to a specialized wind tunnel, but some of the things like P, Q, R, all these other sort of secondary or dynamic effects, you probably can't get those. In a wind tunnel, you'd have to go to CFD, so we are going to leave these out of the discussion. We'll leave these out just due to time restrictions, and we'll leave these sort of dependencies out just because we can't really get those in a traditional wind tunnel. Okay, so we'll do that we'll look at the forces and the moments, and again, maybe we should be a little more explicit. We're going to start thinking about these like in the wind frame, right? Like we said, expressed in the wind frame. So really all we're talking about is the aerodynamic forces. Really we're talking about the coefficient of lift, the coefficient of drag, the coefficient of side force, right? And for the moments we're really looking about the pitching moment coefficient, the rolling moment coefficient, and the yawing moment coefficient. So let's examine how all these are a function of angle of attack, angle of side slip, and maybe I'll just call them delta U for all the control surfaces, right? So that's what we're looking for. All right, so why don't we go ahead and get started? Let's go ahead and look at the coefficient of lift to begin. All right, starting out with our coefficient of lift, what we're probably going to want to do is basically just sketch out a couple of plots, like what does CL look like versus alpha? And let's start with this. This is probably the easiest plot to start with. Okay, couple of things. We should probably ask ourselves, where does this start at, say, alpha equals 0? Right? And again, this can go into a whole undergraduate course just talking about this plot basically. But, long story short, I think everyone will hopefully remember, if you have things like, let's just draw ourselves an airfoil again, and I'm not going to draw, I'm a kind of horrible artist, right? So here's my airfoil. I'm trying to draw a symmetric airfoil, basically meaning it is symmetric about this plane. The top and the bottom of the airfoil is the same, right? So theoretically, right, if you had a pure two-dimensional airfoil and maybe your wing was the only thing on your aircraft, this object, right, as you vary angle of attack, here's a picture at angle of attack 0, right? Here's V infinity from the wind, right? I think everyone will agree that since this thing is symmetric, right, there's going to be no lift generated in this situation, right? So in this case, I think everyone would agree that your plot would start here at the origin, 0, 0, right? Now, what if your airfoil was not symmetric, right? What if you had a cambered airfoil? Gosh, again, I am a horrible artist, so don't take... Go look up a real NACA, 0012 airfoil cross section. In fact, here, let me flash up a screenshot of some symmetric and cambered airfoils, because again, I'm not doing this thing any justice. This looks like a banana to me, but anyway, here's the wing, right? Again, in this case, angle of attack. This starts bringing up another kind of philosophical discussion. How do you define angle of attack, right? A lot of people are going to define angle of attack as a point between the trailing edge and the leading edge, right? And I tried to make these things, I was trying to make it so there's a 0 angle of attack, something like this, right? So this arbitrary line, right, we look at how the angle between this line and the wind, right? And in this case, you see the angle of attack is still 0, but in this case, because the airfoil is cambered, you're actually going to get a net effect lift right, at this point, right? So for this type of airfoil, even at 0 angle of attack, the plot might start up here, right? You start generating some non-zero lift, right? And most aircraft have a wing that is cambered or at least not symmetric, right? So this might be a better place to start off with. Even if you had a symmetric airfoil, right? You have this symmetric airfoil mounted to the rest of this aircraft, which is definitely not symmetric top to bottom, right? So again, you got to remember this CL, this is the aerodynamic CL of the entire configuration, not just the wing, right? So really, in most wind tunnel cases, I would be kind of shocked if you were to get a point that goes exactly through the origin, right? Even if you had a symmetric airfoil, the rest of the body is not symmetric, which will probably give you some net lift up or down depending on the configuration here at 0 angle attack, all right? So anyway, long story short, this is probably what it looks like. Let's go with this one just because, like I said, this is probably the more traditional effect or thing that you're going to observe in a wind tunnel, right? Okay, so here, this is sometimes referred to, this point is, some people will call this your CL at alpha equals 0, or your 0 angle of attack lift coefficient, right? Now, we got to ask ourselves, as we start increasing the angle of attack, what is the lift going to do, right? So, I think everyone will probably agree, you know, here's my very simple example. here's my fan, right? And I'm going to turn it on. And right now, this is 0 angle of attack, right? And now, as I start increasing the angle of attack, this is my poor man's wind tunnel, right? I'm feeling the aircraft increase. It's trying to lift up. It's trying to go up, right? So, I think everyone will agree with the fact that for most situations, as you increase angle of attack, you also increase the amount of lift and therefore the lift coefficient. So this actually goes up. Okay, and surprisingly, this thing is fairly linear, actually. So this thing is just going to keep increasing, right? But at some point, this can't go on forever, right? Usually, I don't know, depending on your design, between 15 and 25 degrees, somewhere like that, you're going to start it's going to start rolling off. This is going to start slowing down until you get to a flat spot, and then you actually will start losing lift here. Okay, so this part down here is sometimes referred to as your linear region. Okay, and this area over here is sometimes referred to as your stall region. Okay? And the point up here, again, stall is sometimes defined differently. Most people define it as your maximum lift coefficient up here before you start losing lift coefficient. So this is sometimes referred to as alpha stall, or the critical angle of attack, alpha crit, however you like to think about it. But it's basically the maximum angle of attack that if you go any further pitched up, right, relative to the wind, you're going to lose lift coefficient, right? So this is probably the plot that you're going to see most of the time. Some people might even extend this backwards, right, because you want to capture some of that behavior, right? So this is your classic lift curve slope. So this is your coefficient of lift versus angle of attack. A couple other things to maybe call out. In this linear region, what's fascinating is this slope of this is sometimes referred to as your partial CL partial alpha, or DCL D alpha, or some people just call this thing CL alpha. Right? This is sometimes what's referred to as a stability derivative. We're going to see these partial derivatives show up a lot, where you're looking at how does a certain variable change with respect to another variable. So in this case, I want to know how does the coefficient of lift change as I change angle of attack. That's very critical for those of you who are stability and control engineers or GNC engineers. This might be critical. We're going to see why later. But some people refer to this as CL alpha. And what's I think worth a couple of minutes discussion is, you may hear some people say, oh yeah, the CL alpha for this plane is blah. They make it sound like it's a static fixed number, right? Really what they're talking about here is that the CL alpha, it is a fixed number here in this linear region, right? But obviously this partial derivative, right, that changes, because I mean over here, for example, right here at alpha stall, this CL alpha is actually 0, right? So what I'm getting at here is that this CL alpha is actually a function of alpha, right? As you change the angle of attack, the slope changes. Sure, it is constant for most of the time, but once you get here into this stall region, it actually starts decreasing all the way to 0, and then the slope actually goes negative. Right? So again, keep this in mind. This CL alpha is really not constant, even though a lot of times in wind tunnel talk or other aerodynamicists or other people, they might make it sound like it's a constant. It's not really a constant, right? This is what we're referring to as this slope, right? Now, what's interesting, I did want to point this out. This CL alpha is in the linear region. Is actually it's fascinating. This is a lot of times it's for most configurations, almost regardless of your aircraft, this slope is pretty darn constant. In fact, for a two-dimensional airfoil, if you had an infinite airfoil, if we're not talking 3D effects, this is typically around 2 pi. And again, the units of this are unitless over radians. Okay, so what's kind of fascinating about this is, again, CL is a dimensionless coefficient, right? And if you measure your angle of attack in radians, this slope for a lot of situations comes out to be about 2 pi. Again, I found this pretty darn fascinating because, again, this is like independent of a lot of other parameters like how you shape it, all that kind of stuff. For the most part, most of them come out to be around 2 pi, right? So what you're buying with a lot of these different airfoils is different stall regions, different CL alphas, and sure, when you have a 3-dimensional wing, or again, this is for a 2-dimensional wing, if you had a 3-dimensional wing, of course you buy different things, but again, this is just an interesting kind of anecdote to kind of mention. Okay, so yeah, that's what I wanted. Oh, okay, so that's one thing to mention. While we're staring at this plot, right, one thing you may want to start thinking about now is I also want to think about what should the data look like, but also now, since we're talking about this in the context of wind tunnel testing, you may want to start thinking about, does this behavior have any ramifications on your wind tunnel test design? So for example, like if this is the theoretical picture you should be getting, one thing you might want to think about if you're designing your wind tunnel test is you got to make sure that you test through the range of angle of attack that you care about, right? So in this picture, you might want to make sure you test from down here, like here's your alpha minimum, right? And then you probably want to capture past stall, right? Alpha max. So you probably have to capture data points all the way through here. Now, the other thing now to think about, right? Just like we talked about, this is mostly linear. There's probably no point in taking tiny little steps in the linear region. You can take big steps in alpha in the linear region and maybe only collect data here, here, probably at 0, sure, here, here. Right? Because otherwise, if you collect really fine data points, you're wasting tunnel time, right? You're wasting it's going to take you longer to collect an alpha sweep, etc., etc. But now, when you start approaching stall, in order to capture this behavior, now maybe you got to start taking finer times alpha steps in order to capture that data properly, right? So you may want to think about this if you're designing a test, that your alpha sweep flag, you probably don't want it to be just a linearly spaced set of alpha points. You can probably get larger alpha points here and then finer alpha points here in stall. Okay, now what's interesting is, again, you've probably seen this curve a million times in your undergrad class, but they probably only drew it to look like this, right? They wanted to show the linear region, they wanted to show stall. Well, again, this alpha max, this might only be, I don't know, 25 degrees. And this alpha min might be, I don't know, minus, I'll make up some number, minus 10 degrees, right? That's a very small region of the flight envelope, right? What if you had an aircraft that was highly maneuverable, like, I don't know, like this fighter jet or something like this, right? It's very possible that maybe you are doing some crazy maneuvers where you have a huge angle of attack, either up or down, right? You're maneuvering all over the place. So this small 35-degree range, that's a very small fraction of the full 360 degrees of what a vehicle can do, right? This is 10%-ish of the entire possible orientation of angles of attack. So maybe you actually need to go out further, right? And one thing that you never see is people usually don't ever draw the extra points, but why don't we just sketch it and think what could possibly happen? You know, in some vehicles, for example, if you keep increasing this, sure, this might keep going down, but some vehicles you might actually get some recovery where you actually start getting lift again if you can just push past this small region, right? Now, similarly, what about in the backwards? What if you keep pitching down? You pitch down, 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 down. So again, you've got your aircraft, and now you're pitching downwards, so it's almost like you're gonna hit this sort of reverse stall to the fact that, you know, right now there's some lift going down. I pitch down a little more, the lift force is even more force down. You go a little more, it's even more down. This can't keep going on forever, so eventually when you reach some critical negative stall angle, the downward force actually decreases, right? So what I'm getting at is this plot might look like down, 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 but then flatten off and then actually come back and stall in the other direction. And then maybe you even get this reverse behavior, right? This thing comes back again. Right? So again, this is actually fascinating because, you know, if you think about this long enough, you probably never see these outside regions because everyone only draws in here because that's where the vehicle is operating 99% of the time, right? However, what if you are in this situation where you've got a drone or something like that where it could be, you know, you want to take advantage of some of these crazy nonlinear behaviors, you may need to capture a lot more, a wider portion of the envelope, right? Again, that's going to cost you a wind tunnel time, right? The reason you don't do this, or the reason why most people test within this small region is because, again, it's going to cost you time, money to get all of these data points out here because you're going to have to take a lot more alpha points. Furthermore, think about this from a mounting perspective. How are you going to make a model? Most wind tunnels, you know, the pitch arm that is driving this thing to make the angle of attack change, you might only have 30 degrees of motion. It's not going to be able to how are you even going to flip the vehicle, you know, way over if that's what you care about? You're probably going to have to stop the tunnel, remount the vehicle in a different configuration and test it again. So again, just interesting things to think about where now we're kind of marrying the theory with the practical implementation of how you're going to get this tested in the tunnel, right? So again, that's just something interesting to think about. Okay, let's keep going with this. Okay, so this plot right here in black, this is probably here at beta equals 0. Right? Would everyone agree that usually the plot that you're going to see here is when the aircraft is pointing straight into the wind and you do this curve, right? But the whole point of having a wind tunnel is I want to maybe ask, what if the angle of side slip is not 0, right? What is that going to do to your lift coefficient? So maybe what we can do, let me erase this. I'm going to kind of make another sketch out here. And let's actually look at also, how about CL versus beta, right? So at beta equals 0, I sure hope that most aircraft designers, right, you're going to be, you know, depending on your angle of attack, I don't know, let's pick an alpha here, sure, alpha 0. So if alpha is 0, you know, if I follow this over, you know, you're probably around here. Okay, so this point right here, this is at alpha is equal to 0 and beta is equal to 0. Okay, so this is literally, you know, if the wind tunnel is blowing straight at the vehicle, oh, you probably can't see that here, straight at the, well, whatever. I think you get it, right? It's just facing straight at the wind, right? Now, we want to ask ourselves, what happens to the lift coefficient if you were to like yaw out at some different beta angle, right? So most aircraft, I think you're going to see have a tendency to lose lift as you yaw out. So if I yaw it in the positive direction, this thing is probably going to start coming down, something like this, right? And actually, I don't know if you would ever actually go negative. Maybe I should be careful with this, right? Because in order to go negative, I mean, it's very possible you could get negative lift, but not for most configurations. So maybe let's be a little more careful. Let's just kind of draw it like this. right? Where you're basically going to lose lift as you start yawing out, right? Now, how does that look like over here on this curve, right? So what we mean is that here is the lift at this point here, again, was alpha equals 0 and beta equals 0, right? But now, what if beta is not 0, right? Oh, and sorry, I should have explained this over here. Right, I drew this symmetrical, right? Because from an aerodynamic perspective, a positive beta is the same thing as a negative beta, right? Because we made this assumption that the aircraft is pretty much symmetric about that XZ plane, it's not going to matter if you yaw to the left or the right. It doesn't matter if the wind is hitting the left side or the right side of the aircraft. You're going to have the exact same effects, right? So that's why I try to draw these two things symmetrical, right? So what I'm trying to get at is, maybe let's draw it in a different color, like blue or something like that, is, again, if you yaw out at a different angle, you lose some lift. So you're probably going to be down like here, right? And now what we're going to ask ourselves is that, here's what we were doing earlier, right? It's straight onto the camera. Again, pretend the wind is coming out of the camera and into the vehicle. Now, earlier, the black line is when we just did this alpha sweep, right? From some negative to some positive angle. Now what we're asking is, what if you yawed the model out to some angle of side slip and then did this alpha sweep from negative to positive, right? So what you would probably see is this curve would be very similar. I mean, they're not going to be completely parallel, but they would probably be similar. Okay, so I'm going to try to draw it as best as I can, and again, let's keep it in this. Maybe let's just keep it in this region. We don't need these crazy extreme regions. Let's just leave it between alpha min and alpha max. Right? So this one, this blue curve, might be for some beta greater than 0, some positive 5 degrees or something like that, right? And that would be something like, I don't know, out here. Here's 5 degrees, right? Okay. And now, what about if you had a negative 5 degrees? Let's draw this in maybe red. Okay. Minus 5 degrees, right? Well, it would be the exact same. The blue and the red curve would overlap, right? For that exact same reason that we talked about, because they are aerodynamically symmetric, right? So the blue is for beta is less than 0, like negative 5 degrees or something like that, right? Right? Okay, and then maybe we can draw like the parallel curve over here, right? So this blue curve was your CL versus beta curve when alpha is equal to 0, right? And then maybe for the blue, let's draw the blue curve when alpha is greater than 0. So when alpha is increased, right? That means we're climbing up this curve. We're gonna generate more lift nominally, right? Something like this. Right? And then again, we'll have the same effect that if the angle of attack is something positive, right? And now we do a beta sweep, or we do a side slip sweep where we start here, take data, take data, take data, take data, take data, 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 right? You're still going to get maximum lift when you are faced straight into the wind, and it's going to then decrease. And again, these are not necessarily parallel, right? There might be some secondary effects that make them shrink or whatnot, but this again is, this is your alpha greater than 0 curve. And then again, same thing, let's look at an alpha negative curve, right? So if alpha is negative, we're down here, right? So now we're saying angle of attack is negative, you're actually producing like less or almost negative lift, and then you do your beta sweep, right? So again, in this case, I think it would be very possible that you might start here negative, right? Because you're already angle of attack down, and then again, as beta increases, you'd probably see something like this. So again, here's your alpha less than 0 curve. Right? So again, I'm just hand sketching this, and we just want to talk through what we might expect, because I think that's helpful. Okay, so that's some of our dependence on angle of attack and angle of side slip. Now, what's interesting is, let's talk about the other deflection that we may care about, or the independent parameter. What about control surfaces, right? You've got many control surfaces on these aircraft. You've got flaps, ailerons, rudders, elevators, throttles, spoilers, all these kind of things that you can tweak on your aircraft. How would these affect these curves. So for example, how about flaps, right? If you were to dump flaps, I think everyone would agree the point of flaps, what are flaps supposed to do, right? Flaps are supposed to temporarily, they're supposed to increase your coefficient of lift at the cost of drag, right? So in this picture, right, again, the black line is sort of our nominal case, right? That's our beta equals 0. You're just flying straight into the wind and you're doing this alpha sweep. Well, what if you did that exact same alpha sweep, but you had dumped the flaps, right? So the flaps are typically what they're going to do is they're going to shift this entire curve up. And again, it's not necessarily going to be a pure shift, like linear shift, but I'm going to kind of draw it as such right here like this. And flaps are probably going to start messing with your stall region. So again, I'm going to kind of, I can't sketch this with enough fidelity, but it's probably going to change your stall angle of attack. It's going to probably change a lot of stuff, but for the most part, right, this curve, this shift to green here is due to a positive delta flap. And again, what I mean by a positive delta flap, we got to be a little careful with our sign convention, our SIGN convention, right? A positive flap angle, in this case, I'm making that sound like it is a trailing edge of the flap going down. So it's deploying the flaps. I've really never seen a situation where you would want the flaps to go in the other direction. I guess maybe that's like a spoiler or an air brake kind of thing. But long story short, you increase the flap angles to increase your CL. And again, that's just almost like an arbitrary sign convention. It's maybe the convention you're going to see a lot, but just something to be a little bit careful of is make sure you define what is a positive control surface deflection. We're going to see with ailerons or elevators or rudders, this gets a lot more arbitrary. With flaps, I think it makes a lot of sense to say positive flaps mean trailing edge down because that means an increase in lift in the most case, right? So, flaps might change this, right? So this might be, let's make up some number, I don't know, 5 degrees of flap, right? Positive 5 degrees, maybe I'll add that, right? Okay, are there other control surfaces? So for example, like what if you deflect the rudder? Well, the rudder, you probably don't expect the rudder to do diddly to this thing, right? Because the rudders are sitting here on your vertical tails. You deflect the rudder, it's not going to change your lift a lot. It might change it a little bit. I mean, I would expect some change, but I would not affect a strong effect. So even no matter what rudder deflection you have, I would expect it to still follow this black line, right? Now, what about things like your elevator, right? Aren't elevators like basically little flaps, right? They're just not as big. So I would expect the elevators to do something. So the elevators might do, oh shoot, I ran out of colors. Maybe let's keep using green for control surface deflections. So the elevators will probably do something to this. Now the question is here, we return to this discussion of which direction is it going to go? If we draw the aircraft, let's just pick some convention maybe. So here's the main wing. Whoops. Here, tell you what, it's over here. Let's augment our picture over here. Where's our horizontal tail? I forgot to draw our horizontal tail. Let's draw it over here, okay? Okay, so we said a positive flap angle is like this, right? So here is a positive delta flap, right? Why don't we use the exact same convention, maybe? Maybe we should say positive aileron angle, or excuse me, positive elevator, delta E. Actually, you know what? Well, okay, this is where it gets arbitrary, and this is where I'm shooting for a little bit from the hip because the sign convention is not fixed in any particular fashion. Let's just go with this. We're going to see down the road this may have some... Actually, you know what? I do want to flip this because I think in our other lecture we may have... yeah, let's call a positive flap angle or elevator the other direction. Let's call this a positive delta elevator. Okay, and we'll see why later. But again, this highlights again this thing that we need to be careful with the sign convention. So in this case, a positive elevator, look at what is this going to do to the tail, right? It's actually going to kind of make the net lift of the tail go down, which counteracts the main lift of the wing. So long story short, a positive delta elevator is actually going to decrease the amount of lift on the overall configuration. But since the elevator is usually much smaller than the flap, I would imagine for this same, if we chose the same deflection of 5 degrees, I actually think it's probably going to do a lot less effect. So I would expect something like, oops, wrong color. I'm trying to use green for control surface deflections, right? Something like this, right? So this delta here is due to your positive delta elevator of also this plus 5 degrees, right? It's going to make your lift curve go down, but not by as much, right? Okay, and again, I think this is just for one dimension on CL, and I think we've actually kind of beat this to the ground. We are going to see, let's keep these flap and elevator, all those deflections in mind, because like we said, it almost looks like you got something for nothing here, right? You dump the flaps and you just bump up the lift coefficient and everything seems to get better. Well, that may be true from a lift perspective, but what about from a drag perspective? So give me a second to erase the board and let's move on to our next force. Let's ask, how about drag? All right, so let's move on now to our coefficient of drag, CD. So again, let's draw ourselves a little plot, maybe CD versus alpha. We can start with that. Okay, so let's think about this. What should this probably look like for a normal aircraft? So the aircraft is probably going to have some trimmed angle of attack, meaning the aircraft designers have made it so that when this is flying along, straight and level in cruise configuration where it's going to be flying for, 98% of the time, it's got some small angle of attack probably so that it makes enough lift to counteract the weight, and this thing will just fly along nice and straight, right? So again, it's probably got some small trim angle of attack. So why don't I denote that, let's say, I don't know, maybe out here. Let's call this alpha trim, okay? Now, if your aircraft designer was competent and smart, what would you probably want? If you're flying along at your trim angle of attack, you probably want to design this aircraft such that since it's doing this for the majority of the flight, right? It's just cruising along straight and level at this trim angle of attack. You probably want drag to be at a minimum at this location, right? So this is probably the minimum value. You're probably not going to get zero drag, right? But you'll probably have some minimum here. And now, as you start at this point and you start increasing angle of attack, right? You're flying along here, and if you increase the angle of attack or you decrease it, I think everyone will hopefully agree that what's going to probably happen is this is just going to go up, right? And probably in both directions, right? So you probably have the minimum drag here at this alpha trim, right? That's probably what's going to happen, right? Now, okay, so this is what CL alpha might look like, and again, this is probably for your beta equals 0 case. So let's just quickly sketch out also, what might CD versus beta look like. So again, I think it's easy to think about from the beta equals 0. If you are flying straight into the wind, again, hopefully your aircraft designer has made it so this aircraft has minimum drag when it's flying like this, right? Because again, you're in your trim angle of attack and you're just flying straight along, and this probably has minimum drag. If you were to crab out in either direction, right, most aircraft will probably start incurring a drag penalty if for any side slip angle that deviates from 0. And again, this thing is probably symmetric, right? So again, this is your very classic drag polar of where you are probably, again, going to have some minimum drag number, and then this thing is just going to go like this, right? And again, this is probably, the black might be for the alpha equals 0 case, right? And we can obviously ask ourselves questions of how do either one of these two curves change if you have positive cross terms. So for example, coming out here at alpha, let's look at what might this curve look like for a positive beta, right? So a positive beta, again, you're probably not going to get this minimum drag. You're going to have some penalty like this, and again, it's probably going to shift the curve something like that, right? So here is beta positive, and again, due to that symmetry we discussed earlier, the beta negative is probably going to be lying exactly on top of it, right? So here the red is beta is negative, right? And you could ask yourself, same thing over here, right? What's interesting about this though is, again, here's your alpha equals 0, or you know what, might actually be, well, I guess we can think about this. The difference between alpha 0 and alpha trim is small. Let's call them about approximate. Let's just say you're deviating from alpha trim. It really doesn't matter. We're really talking back of the envelope calculations on what should probably happen. But long story short, your drag is probably minimal here when you're near this alpha 0 or alpha trim, right? So anything above that, so let's again do blue for above. Again, your drag polar is probably going to just increase, right? So here's at alpha positive. So yeah, you probably get more lift as you increase angle of attack, but the penalty you pay for that is more drag at pretty much all side slip configurations. And again, if you decrease the angle of attack, you don't decrease drag. You actually still probably incurred a drag penalty. And now here's where it probably is not the same, right? You're probably going to get some other drag polar. I don't know. I'm going to just sketch it, you know, something like that. Again, we're just shooting off the back of our hip right here because we're just trying to guess at this effectively, just roughly estimate what we should see. Okay, so that's probably what these drag polars will probably look like as you vary alpha and beta. How about these control surface deflections, right? We talked about this earlier, like how about the flaps, you know, right? We were talked about dumping flaps, and that got you a whole bunch of lift increase kind of almost across the board. So it looked like from a lift perspective, flaps were a no-brainer. You want to pump that up. Well, the problem you're probably going to see is that when you drop flaps over here, your drag is probably going to go up for a ton of these alpha curves. In fact, it might be something drastic, like it could do something like this, right? So here's a deflection of, you know, like some positive delta flap, right? So you pay a huge penalty. Again, also similar over here, right? So here's maybe like your delta flap, right? A flap deflection is probably going to cause you a giant increase in drag. So here's maybe why, you know, you're not flying around with flaps all the time. You're using flaps for takeoff and landing, where you're okay to pay a little bit of extra drag penalty for that increase in lift, because you're only doing it for 1% of the flight, right? The rest of the time you're gonna pull these flaps in, and you'll be able to recover back to this black curve, right? Which has much better drag. And again, pretty much every single control surface deflection, right? Delta flap is probably going to give you more drag, like a delta elevator, right? A delta elevator, it's probably not as drastic. So again, let's say this is plus 5 degrees flaps. That gives you a huge penalty in drag. A 5-degree elevator deflection might only do something like this, right? So here's like the same run for delta elevator of positive 5. Right? And same thing, you can think about this, rudders, spoilers, you know, pretty much any control surface deflection, I think you would probably expect an increase in drag, with kind of one exception. Think about this for a little bit. This wind tunnel model is just mounted on the balance, right? So the balance is just sitting in here, right? The balance, you can almost think about this is again, here's my poor man's wind tunnel. Let's turn the wind on, right? Oops, I just knocked off this stabilizer. It's a problem with these old toys, they don't hang on very well. Okay, right? So you've got the wind tunnel going like this, right? My hand is like the wind tunnel balance, and I'm gonna close my eyes, right? Because I don't even know what's going on. All I know is that the aircraft is at some configuration, and all I'm doing is I'm feeling the force. So now let's pretend, right, you dump flaps, right? As you can see on that curve, you deflect the flaps. Oh, I feel the drag increase, right? So that makes sense. Okay, now you deflect the ailerons. I feel the drag increase a little bit. So again, the drag increases, right? That happens for every single control surface deflection. But here, what if you have a powered model, right? What if your aircraft has your wind tunnel model has engines on it, like a nacelle or a propeller or something like that? What happens if you deflect the throttle setting? Now I close my eyes, they deflect the throttle setting, and whoa, I feel the aircraft almost pull forward, right? The drag actually decreases. So what's fascinating about this is there might be a situation where if you have like a throttle, like I said, propulsion, maybe you might even get something like this, right? Here is delta throttle, is like what let's call 1.0. You crank up the throttle to full throttle, and you get something like this. Look at this, you get negative drag. you might be tempted to call the patent office at this point. If you see a drag curve that looks like this, and you see negative drag, that, you know, yeah, call the patent office. If you've come up with a configuration which gives you negative drag, that's awesome. But it's also a little misleading, because really, all this is a function of the fact is that the wind tunnel, the balance is just measuring the sort of like the axial force in the wind direction, right? Most of the time, it's got drag pulling it, right? But if you've got propulsion, if you've got engines, if you've got thrust on this thing, and you crank up the engines, yeah, sure, it's very possible, right, that it could have a net resultant force in the positive direction, which is really negative drag, right? It's because the wind tunnel model doesn't care, right? It's not, or the balance, it doesn't care, right? It's not honey badger don't care, right? It's wind tunnel balance don't care. Wind tunnel balance just measures the net force. So if you have a powered model, it might be possible that this what you're calling drag, we really should be calling axial force aligned with the wind, right? So you just gotta be a little bit careful of this. Again, yeah, don't go call the patent office. Don't quit your job and run off and start mass producing this, because if you see this curve with negative drag, it might just mean that it corresponds to like a power test, where in this run configuration you had throttle on, and the throttle was enough to counteract all of the aerodynamic drag of all of the body, all the control surfaces, all that kind of good stuff. So again, I just think that's a little fascinating side note that maybe we should talk about. And again, I think overlaps with this discussion of you know, do you want to do powered wind tunnel testing, right? Are you going to have a model which has an actual propeller on this, right? If you have like a UAV or a drone or something like that, where you could actually fit the entire vehicle, engine, propeller, and everything, and all in the tunnel, maybe that's what you want to do. Is maybe you want to turn on the engine and understand some of the effects on the drag due to the engine. Okay. Okay. Let's see if I wanted to mention anything. Yeah, I think that is that's good for drag. Okay, let's move on to Sideforce. All right, so Sideforce, this is an interesting one. Why don't we start here with the CY versus alpha, and let's look at, again, we'll use black to denote the beta equals 0 case. So again, this is now where the aircraft is just pointing into the wind, and we are now going to do a alpha pitch sweep like such with 0 side slip angle. And as you can see, right, the aircraft is symmetrical about both sides. So hopefully during this entire run, I think everyone would agree there should probably be no side slip at all on this vehicle, right? So at beta equals 0, this thing is probably just flat, right? It better be flat, right? So this is the beta equals 0 case, right? Now, where it gets interesting is let's look at how about CY versus beta? What's going to happen? Let's come back to this picture. This is a picture we've drawn for a positive beta, right? The wind is hitting the right side of the aircraft, right? Now, I think everyone would agree that from looking at this picture, wouldn't sort of your net resultant side force sort of be in this direction? Right? Because the wind is hitting this side of the vehicle, it's going to kind of shove it in that direction. What's interesting, this is actually in the opposite direction. How did we define a positive side force in the wind tunnel? So the wind tunnel is probably going to give you, this is a positive side force. So what we see here is that a positive beta actually yields a negative side force. And you can see as beta increases, this actually gets, the force probably gets more and more pushed like this. So long story short, you probably start here at 0. We talked about this already. At beta equals 0, you got no side force anywhere. But as you increase beta, this actually becomes negative, right? Something like this. And now, what's actually even more interesting is if you think about this, what happens if you keep increasing beta? If you think about this, this is almost like the lift versus alpha curve, because really all you're doing is, you know, you're increasing, and then it's effectively, it's gonna stall in the other direction, right? So same thing, this thing is gonna keep going out, and then it's probably gonna stall, and same thing, it's symmetrical, right? It's probably gonna stall something like that, right? So anyway, here's the alpha equals 0 situation, right? So it's actually kind of neat. Now, what about some of these cross terms, right? So again, let's do an alpha sweep at a non-zero beta. So now, we're getting here, let's go ahead and do this at a, okay, here's positive beta, right? Because the wind is now hitting the right side of the aircraft. And now let's go ahead and do an alpha sweep, right? So again, in that situation, I think it's a little bit more slightly unclear. So I think we were using blue for the positive. So at a positive beta, we saw that ends up with a negative side force. So it's probably something like this, right? Now, the question is, as alpha increases, right, as you start pitching up through that, I'm not entirely sure if this is going to, which direction this is going to go. I mean, maybe it goes up like this, maybe it comes down, you know, who knows. All we know that this is pretty much for beta greater than 0. And then similarly, you would probably see a symmetric kind of effect just in the other direction. Gosh, I'm not a good artist. I think we saw that. There we go. So this is now for the beta less than 0 case, right? And then I think we can make a similar argument over here on if you did a beta sweep at a non-zero alpha. Again, this is probably going to look something, you know, it could be like this, right? It could be more gentle. So again, you know, who knows what this is going to look like. It's this red here, I think what we're using, this is alpha negative, and then blue would be for alpha positive, right? It could do something like this. Again, you get to kind of pick, right? And it could be configuration dependent, but you'll probably have this trend in the sense that for most of the regions, you're looking to see something like a partial of CY, partial beta, right? This is effectively the slope, right? Again, some people you might see this referred to as CY beta, right? This is probably going to be negative for a large portion of the envelope, right? For your operating envelope. And again, it's the same thing with that CL alpha discussion we have. Keep in mind that CY beta, some people might talk about it like it's a constant, but really it's the slope of this at any given location. And as you can see, that depends on alpha, that depends on, you know, your beta, all this kind of stuff, right? Okay, how about control surface deflections? Let's go ahead and talk about that real fast. Let me erase some of these. Okay. How is the control surface deflections going to change any of these? So I think we can probably safely assume that most of them, like the ailerons, the flaps, the elevators, the engines, the throttle deflections, they probably don't influence the side force component, right? But I think everyone will agree that the rudder will probably do something to this. So again, this is where we get, I don't want to say bitten, but we got to be careful about the sign convention again. So let's just draw, again, I will just arbitrarily pick a direction. Let's just call, how about trailing edge of the rudder to the right? Let's call this a positive delta rudder. Whoops, I didn't draw that very well. Okay, so what is that going to do? This positive rudder deflection, again, this almost is like a mini wing that we've now made cambered, right? It's a symmetric airfoil, but then we've kind of made it cambered. So a positive rudder deflection will actually make the tail kind of go like that, right? Which again is opposite of the positive side force. So I think what you would expect in this situation is that the rudder deflection is actually going to yield a negative side force. So here's maybe your beta equals 0. Let's say you did the beta equals 0, right? We see exactly 0, right? Okay, and then you do this alpha sweep, but you do it with a positive rudder deflection. If this is our sign convention, I think I would expect something like this. And again, this isn't maybe this goes up or down, or you know, the rudder might be differently effective at different alphas, right? So just again, something to keep in mind. Here's like a positive delta rudder, right? And you can probably do a similar analysis over here on the side force versus beta, that the rudder is going to probably offset this in one direction or the other, probably in this case the negative. So again, you know, something like this. Here's like a positive delta rudder, right? Okay, great. Okay, so side force. So actually, I think we got all of the forces down. So at this point, I think we have a reasonable idea of what all the forces are going to do. Why don't we move on to the moments then? All right, so how about the first moment? Pitching moment is typically your classic one that you're going to be looking at to start off our discussion on moments. So let's look at coefficient of pitching moment versus angle of attack, right? And what you will typically see is for a lot of stable configurations, you're going to see a configuration that looks something like maybe like this. Okay, and again, what you've hopefully done is you've designed, or your aircraft designer has made it so that the place where it crosses zero, this is your alpha trim. The reason this is called alpha trim here is because if you're at this angle of attack, notice here that the pitching moment is equal to 0. So what that means is there's no tendency for the vehicle to continue pitching nose up or pitch nose down, right? There's no tendency at that configuration, right? And maybe I should orient it in this way so the aircraft is in the same direction as this picture we've got, okay? Now, in this configuration where the slope of this curve, right? Again, we're back to this discussion on slopes and stability derivatives and partial derivatives and all this stuff. This is sometimes referred to, right, as your partial of coefficient of pitching moment, or DCM, D alpha, right? Or again, which is CM alpha. Okay, so you might see this referred to it. And what we see here is in this picture, this is negative. Okay, the reason it's good to have this thing negative is because if you're sitting out here at alpha trim and you're just flying along, right? And let's say a gust of wind or something like that comes and bumps it so the angle of attack increases. Either the aircraft gets knocked up or the wind vector changes slightly, but long story short, let's say that your angle of attack increases slightly, okay? What that means is you'll be out here, right? A little bit above your trim angle of attack. Well, if that's the case, look at this. The coefficient of pitching moment is negative. So that is going to have, according to our sign convention, right, a negative pitching moment means nose down, right? So this is a restoring moment that will kind of push you back towards alpha trim. Similarly, if the gust pushes you in this direction, so now instead of alpha trim, you're a little bit less than alpha trim, you now have a positive nose up restoring moment, which is going to put you back in the trim location. So this is what you might see if you had a stable configuration, at least stable longitudinally. And again, this is a very hand-wavy back of the envelope discussion on dynamic stability. We will get into a much more robust discussion on dynamic stability when we actually build our aircraft model. But long story short, this is what you would probably see in the wind tunnel. Now, that brings up an interesting point. What if you don't see this, right? If you had something that was the other way, right? It's almost the converse discussion. You might almost say that this is an unstable configuration. Now, before we jump to conclusions there and condemn this data, if you see this coming out of your wind tunnel, you might just throw your hands up and say, oh, test is over. We've screwed something up. We need to go back to the drawing board. Well, that may or may not be the case because now, if you remember from our previous discussion, on data correction and reduction, we actually should probably be a little bit more explicit about this. The coefficient of moment is not enough to describe what we're talking about, right? This is the coefficient of moment about what point, right? Remember there's that discussion on moment transfers? Typically what you would want this to be is at the center of gravity of your vehicle, right? Because then you can have all this discussion about saying, oh, that tends to pitch the nose up or down or whatnot, right? But in the wind tunnel, right, you're going to plot this around multiple model moment centers, right? You might project the moment center to be here or here or here or here, right? You get to pick, right? If you see this data, it might just be because the data is coming from another model moment center. If you transfer that moment to another location, maybe this curve is going to start changing and you might get something that looks a little bit like this. So again, don't despair if you have what you think looks like a wrong curve. It just might not be transferred to the proper location yet. So you may have to conduct that analysis, okay? Okay, so what else should we chat about? Okay. How about as beta changes, right? So this is, again, is at the beta equals 0 case, right? So I think in this case, you'll see it's a little bit hard to understand that, all right, or at least hard to predict. You know, you do a normal beta equals 0 sweep just like this, and now you yaw the thing out and do another alpha sweep. How's that going to affect the pitching moment? You know, you probably have this general shape, but does the pitching moment get increase or decrease, right? It's a little bit unclear. So again, let's just sketch this for giggles. Like I will pick something. Let's I don't know, I'll make this up. Let's say it does something like this, right? So here's your beta positive. The only thing that probably is a surefire bet is because the aircraft is symmetrical, we're again in the same situation where if you yaw to the negative by the exact same amount, right? If this is positive phi beta, negative phi beta, they should be symmetrical and they should lie on top of each other regardless, right? And again, you know, if we complete our discussion and we look at our CM versus beta, again, this is a little bit interesting to look at. You know, we can probably say that here at beta equals 0, let's make this black curve your alpha is equal to alpha trim, right? Because we know at alpha trim you have 0 pitching moment, so you might be like this. Now the question is, as you yaw the aircraft out, does the pitching moment increase or does it decrease, right? It's not entirely clear. You may get different configurations. So again, we don't look at CM beta and draw any conclusions. This is a more classic example that's analyzed. Okay, how about control surface deflections? So let's talk about those. Which control surfaces have the potential to mess with these curves? Well, flaps, we talked about earlier, flaps will change this, right? Flaps will probably, depending on which direction, you know, a positive pitching moment, or sorry, a positive flap deflection, a lot of times that does have the tendency to give a nose down deflection. So a positive pitch might be something like this, right? So here is like, or sorry, excuse me, a positive delta flap will influence this. Now remember, we said earlier when we were looking at lift coefficient, we said the flaps definitely mess with your lift coefficient, and the tail or the elevator deflection also changes your deflection, but or sorry, the elevator changes your lift coefficient, but not by a lot. Now, in this case, though, if we're looking at pitching moment, we see that actually this elevator deflection will have a large potential to change your pitching moment, because you see we've got a huge moment arm now, right? There's a moment arm between the center of gravity and the center of pressure of your tail. So in our case, using our sign convention, a positive delta elevator yields a downward force on the tail, coupled with this moment arm actually yields a nose up configuration, right? Or a nose up pitching moment. So in this case, positive delta elevator yields a positive pitching moment, and furthermore, it's non-trivial. So again, a small elevator change might have the potential to take this entire black curve and shift it up by a good amount, right? So here might be the deflection due to a positive delta elevator, right? Okay, now while we're at this, actually, we should also look at, and I want to draw your attention back to the wind tunnel data reduction, where we talked about when you're applying wall corrections to your tunnel data, there was this parameter, we called it DCMDDS. Right? And that was really the partial of the coefficient of pitching moment with respect to the delta stabilizer. Okay, now note here that delta stabilizer is not equal to delta elevator, right? Elevator is just the trailing edge deflection, right? It's just this trailing tab on the stabilizer. The stabilizer angle is the entire angle of this entire horizontal tail, right? So what we have to do here is we're actually in a position now to go ahead and try to measure experimentally this parameter of how the pitching moment changes as I change the entire stabilizer angle. So now this plot is getting a little bit busy. Let's redraw it maybe, okay? Here's pitching moment versus alpha, okay? So we said normally it looks like this, right? So here is the situation. Let's put the stabilizer at 0, maybe like, you know, 0 or your nominal situation, right? Now, what you want to do in the wind tunnel now is to measure this parameter, is you actually want to go ahead and you're going to have to change the entire angle of this stabilizer. So again, let's make a sign convention that maybe this is a positive stabilizer angle. So now I've drawn this here as a positive delta stabilizer, okay? So now, look at this. Again, according to this sign convention, the way we've done this, a positive stabilizer angle is almost like increasing the angle of attack of the tail. So this is going to increase, maybe I should draw this in green again, right? Increase this, which actually corresponds to a now nose down, right? So now, if this is the stabilizer of 0, I'm going to draw a positive deflection. So a positive stabilizer angle there actually goes down like this, right? So here is like a delta stabilizer of like, I don't know, positive 5 degrees or something like that. Right? And again, they're not going to be exactly perfectly parallel, right? They could be a little bit squashed or whatnot, but this is the general trend, right? And similarly, if you do it the other direction, if you go ahead and deflect the stabilizer, and maybe I'll exaggerate it like this, right? Now you exaggerate it and you put the stabilizer in the other direction. So this is, I'm running out of, let me move my axis label so we can read this a little bit more easily. So here's CM, right? Okay, so now this red is a delta stabilizer of negative 5 degrees, right? It's going to do something like this. Now, from this plot, we can actually go ahead and get this parameter, right? So for example, if I wanted to look at what this parameter is, we got to first pick an angle of attack. So let's pick an alpha here, right? Something like this. So what we can do is you can actually see that the rise is in this term. I want to approximate this thing as basically finite delta CM, a change in CM over a change in stabilizer angle, right? So the change in CM is this distance, right? It's here to here, right? It's a vertical distance between the red and the blue line, right? And we see in this case, it's a positive number. Wait, I got to be real careful. Which one are we calling? Yeah. Are we doing red versus blue? We got to be careful of which one we're calling run A and which one we're calling run B. It really doesn't matter. It should come out in the wash as long as we're consistent, all right? Let's do red minus blue, okay? So in this case, shoot, I ran out of board space. I should have managed this a little better. Let me move this over. I'll warp this over here, okay? So this is, so delta CM, right? That is, let's make up a number for this. I don't know. Let's call this, I don't know, 0.3. here, and let's call this number, I don't know, negative 0.1. Okay, so if I'm going red versus blue, the change in CM, it's 0.3 minus negative 0.1, right? Okay, that's the numerator. Now the denominator here, right, this change in stabilizer angle, I gotta also go red minus blue. So red, the deflection here, it's actually negative 5 degrees, right, minus the blue was positive 5 degrees, right? Degrees. So at the end of the day, what does this thing come out to? This is 0.4 all over negative 10, right? So in this case, my partial CM, partial, whoops, gotta get my symbols correct, partial delta stabilizer, right? This is negative 0.04, right? So here is where, you know, if you're looking at your pitching moment data, we can experimentally pull off these things that we might need for wind tunnel data corrections like this DCM DDS. And again, I just also want to point out, notice we talked about these curves aren't necessarily parallel to one another, right? So this value, it's actually, right, we should say that this is a function of angle of attack, right? As you increase angle of attack, right, if you did it out, if it did this same operation out here, and you looked at this distance, this might change. So this is, again, one of these parameters where it's not necessarily a static number for the entire configuration. It can change with angle of attack. It could change with angle of side slip. It could change with all these different things, but in the interest of time and simplicity, most of the time we are going to call this like a constant number. We're going to forget this dependence. You're going to pick some range, and that'll be the parameter that we use for our wall corrections, and this is how we're going to experimentally get it off of these plots. Right? Okay, so yeah, great. Is this pretty good? Oh, maybe the one last thing while we're talking about, I guess, control surface deflections like stabilizer, elevator, you know, flaps, all this stuff. What else might influence this? You know, rudders and ailerons, those are probably not going to influence your pitching moment much, but you could have things like engines. Like, what if you had underslung engines, right? If you had engines down here, right? And these things are producing a thrust, right? I think everyone can see that there's a potential, depending on how much thrust you're having, this will cause either a nose up or a nose down configuration. So these curves could also change, not just due to delta elevator and delta flaps, but delta throttle might also influence these curves. So again, if you've got a powered wind tunnel model, that could influence things as well, depending on the configuration. Okay, great. All right, let's move on. All right, so on to a rolling moment, which again, sometimes you'll see denoted as C little l or CR, whatever you'd like. Okay, so let's take a look at this. Again, I think an easy place to start is C roll. Let's call it, I guess I'll use CR versus alpha. Okay, same situation as some of our things like Sideforce. For example, at 0 beta, I think I would expect this thing to be completely flat, right? Right, because again, this is basically a situation where, yeah, you got no angle of side slip, and all you're doing is just pitching up. Like, since the aircraft is symmetrical, it should not have any tendency to roll one direction or the other, right, during this configuration. So totally flat. Now, before we suss out the other one, actually, let's take a look at maybe C roll versus beta. This is actually kind of interesting. What would this do? So let's come over here to this picture. So if you look at this again, we drew this as a positive beta. With this swept wing aircraft configuration, I think would everyone agree that it sure looks like this wing is straighter, right? And this one is more swept back. Right, at least relative to the air, to the free stream air, right? So the component of velocity that this wing experiences is actually kind of greater than this wing, right? So due to the fact, and you combine that with the fact that this air is actually almost in kind of cleaner air, right? Because the air that hits this wing is kind of dirty in the sense that you've got part of the fuselage blocking it, shedding vortices and whatnot, all that kind of good stuff, or I guess bad stuff technically in that case. I think would everyone agree that probably this wing has more lift than this wing? This has less lift, right? That seems to make sense. So the force vector is going to be coming out of the page quite large, and the force vector that this wing is going to generate is smaller, right? Both of them will still probably be generating lift, but this wing generates more lift than this other one. So what is that going to do? That's going to have a tendency to roll this wing, the right wing, tip up, right? So the aircraft, it's going to want to, I mean, again, you got our picture, you know, it's like this, right? And now this wing is going to want to roll it like that, right? So interestingly, at a positive beta, we have its tendency to roll right wingtip up. How is that set up with our sign convention? I believe we actually had it the opposite. So most wind tunnels are going to have a positive C roll, right? This happens when you have the right wingtip up, right? Because again, that corresponds with usually your Y body axis is coming out the nose of the aircraft. So a positive, wait, oh no, sorry, excuse me, I wrote this exactly backwards, right? Wingtip down, right? Because if your y-axis is coming out the nose and then right-handed rule, yeah, usually that's right wingtip down, okay? So what we see in this case, it's actually opposite, right? So in this case, a positive beta induces a right wingtip up kind of configuration. So what we would probably see in terms of this from CR beta is, again, we know it's going to go through the origin, right? We said at 0 beta there's no roll at any alpha, but in this case we would probably see this something like this, right? So here is at alpha is equal to 0, right? Okay, now that we've got that out of the way, I guess we can start thinking about some of these perturbations, like what if we did an alpha sweep at a non-zero beta, and that, you know, it's kind of anybody's guess about what would happen. So the beta is positive, you know, it might be down here, right? So here's your positive beta run, because again, all we're talking about now is that now we're going to do an alpha sweep, but we're going to yaw this thing out at some, I guess positive beta is like this, right? I want to hit the right side of the aircraft, and now we're going to do an alpha sweep. So you know, what's going to possibly, well, I guess in this case, you're right, this wing we're going to actually have a negative. So actually, yeah, this is probably what's going to have happen, right? Because if you're at a positive alpha, you're going to have a negative beta, so which is a negative roll. Yeah, so it's going to be like this, but the slope of this, I guess, is what's the thing we're contesting. I don't know if this is going to go up or if this is going to go down, right? Does this effect get exacerbated as you go nose up or nose down, right? That's a little bit unclear and probably a second order effect. So yeah, it should probably be down low like this, right? Because if you yaw the model out positive, you are going to decrease the rolling moment. So yeah, it's going to become negative. So it'll be down like this. Yeah, so that one is going to look like such, and it should be symmetrical. Whatever this thing does, it should be symmetrical on the other side. So here's for your beta less than 0. Right? And then similarly over here, we could do, it really is again anybody's guess. You know, you could have something like this, or you could have something like this, right? So here is again your alpha greater than 0, and this one is your alpha less than 0. Again, all we know though is that they should pass through the origin for all of these cases, right? That's this black line basically saying you have no roll at any alpha if beta is 0, right? But again, these could be switched, right? The blue line could be down here, the red line could be up here, right? It kind of depends on configuration. Now, speaking, I guess of depends on configuration, right? We talked about all of this. A lot of this slope is due to this argument that we made, you know, about, you know, having swept wings, which one is straighter, which one is not, right? What if you have, you know, maybe 2 configurations, you know, a traditional swept wing aircraft and maybe like a forward swept wing, you know, would this effect be different? I'll leave that as an exercise kind of to the reader to kind of either do some research or do some analysis and think about a little bit, right? Okay, so I think that's most of the alpha beta dependence. What about control surface deflections? I think everyone would agree that probably the thing that influences the roll the most is going to be the ailerons, right? Because you've got ailerons here on both sides. So ailerons or differential flaps or anything like that which has a tendency to cause a rolling moment will probably change this. And again, it's anybody's guess to which direction depending on your sign convention. A positive aileron, right, might be something like, we'll say, causes a positive roll, but again, it really doesn't matter because all you're talking about is which direction are you calling a positive deflection on these ailerons. So yeah, that's one thing to think about. The other thing that's actually kind of interesting about this as well is, yeah, ailerons are probably going to influence this. I don't think your engines are probably not going to influence roll, right? Your elevator is not going to influence roll, but how about the rudder? This is kind of interesting. Think about this. With the rudder, again, coming back to our picture, we picked a sign convention of a positive rudder goes like this. So this is actually going to create, right, we said a positive force like such. Right? Now, let's look at the geometry of most aircraft. Most aircraft have their rudder something like this, right? Where the rudder is above sort of the CG of the aircraft. So you can imagine that if there's a force on the rudder, right, that pushes this is actually going to have, it's got a vertical moment arm about the center of gravity. So this rudder deflection, even though it mostly causes a yawing motion, it has the potential to also roll the aircraft. So what you might see in your wind tunnel data is that well, let me see, we said a positive rudder in this case is going to go like that, so this is going to tend to roll this thing, so nose, right wing tip comes up out of the page, so it's actually opposite, right? So same thing, we would see like a rudder deflection do something like this. So here's a positive delta rudder, right? You would probably expect that to do some kind of influence some of the rolling motion as well. So it's again, it's kind of interesting that depending on your configuration, you could see these cross-coupling terms coming into your data. Okay. Okay, let's look at our last one. Since we're talking about rudder, let's move on to yaw. All right, so on to our last one, our coefficient of yawing moment, Cn. Again, do not get this confused with Cy, right? Cy was side force, not yawing moment. So let's call this thing Cn. So just sketching this, we're going to look at, again, our very normal Cn versus alpha. And I think everyone will agree we're basically in the same boat as sort of our rolling moment in the sense that due to the aircraft being symmetrical, if I start off with beta equals 0 and I do a alpha sweep like that, I don't think you would expect any yawing moment whatsoever. So this thing better be flat, right? So flat, 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 flat at all alpha. So here's your beta equals 0 curve. Now, if that's boring, how about the other one? How about Cn versus beta? This is maybe less boring because you look at this picture with a positive beta, what's going on down here? So the tail is actually going to experience wind like this. So there's actually a positive angle of attack on this tail, which is going to generate sort of a lift in this direction, right, due to the vertical stabilizer. So while beta is the angle of side slip of the overall aircraft, it's also the angle of attack of the vertical stabilizer, right? So this is going to make a force in that direction, which actually corresponds to a yawing moment like this. Right? So we should ask ourselves, what was the sign convention? If you remember, for the wind tunnel, a positive yawing motion generates a nose right deflection. And again, that's because I think we said our Z body axis, I think, was into the page, right? So here's the Z body axis. Yeah, so if that's into the page with our right hand rule, yep, positive goes that way. Yeah, so there we go. So positive beta gets you a positive yawing moment. And as you increase beta, right, this actually gets, the angle of attack gets increased, so this force actually gets bigger, so the yaw gets bigger, etc., etc. So I think what we can do is we can basically say that, all right, in this case, what we should see for most stable configurations is this sort of behavior, right? So here's your C, this is the alpha equals 0. Right? Okay. Yeah, there we go. Perfect, perfect, okay. So, and again, here's one of these stability parameters or stability derivatives that a lot of stability and control guys are going to be interested in. So here is your partial of Cn with respect to beta, or sometimes referred to, right, as Cn beta, right? And in this case, we see that we want this to be positive for stability because this is the exact same discussion we had with pitching moment and longitudinal stability. Now we have a discussion on yawing moment and directional stability, because in this case, you can see that as you're flying along straight, right, with 0 beta, you have 0 yawing angle. That's perfect. So the vehicle is just tracking straight. It's just flying, 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 and everything is hunky-dory. Now, you hit a gust, and the gust is going to give you maybe a positive beta. Right? So a positive beta is like that, right? So it's going to now, it's flying, but now you've got the wind hitting the right side of the aircraft. Well, now, according to this data, that bumps you up here on the curve. So now you have a positive Cn, which is basically a positive yawing moment, which brings the nose back right, back to center, right? So you see that if you have a positive Cn beta, you probably have a directionally stable aircraft. Again, for mostly, right, for all else considered, right? Okay. How about some of the dependence on, you know, does this exacerbate or change if we do some of these cross terms? So again, let's maybe think about let's do a beta run at a non-zero alpha. So now what I want to do is we already did the beta sweep at 0 angle of attack, and we started, you know, we did this beta sweep and we gathered data. Now let's think about what if we increase the angle of attack and do that same sweep. You can actually almost see it from the camera angle. Let's do the 0. Here's the 0 angle again. Now look at the vertical stabilizers here and here. Notice how they're in fairly clean air, right? As we're flying through this, the air that hits the vertical stabilizers are fairly clean, right? So now let's increase the angle of attack and do this same beta sweep. Look at this. Do you see how you can't even see the vertical stabilizers anymore because they're occluded by the body of the aircraft, right? So I think everyone would agree that at a positive angle of attack, these stabilizers are probably less effective, right? They're in dirtier air, so they're not as effective. So therefore, if I want to draw in blue, let's look at the beta sweep at positive angle of attack. Because they're in dirtier air, this restorative force is probably less, so you basically get less Cn beta. So here's your alpha, greater than 0, right? So you see that at a positive angle of attack, this Cn beta value, right, which is this slope, goes down. So you have a slightly less directionally stable vehicle when you're pitched up, right? And you probably get the, not exactly opposite. So maybe I'll draw it like, kind of like this or something. Right, so here's your alpha less than 0 case, right? Because sure, the red line corresponds to, instead of 0 angle of attack, you have a slightly negative angle of attack, right? So yeah, the horizontal stabilizers are pretty clean, and now you do this beta sweep, so yeah, it's probably still pretty effective. It might be even a little bit more effective, but really this is again kind of back of the envelope discussion here. So, okay. There you go. Oh yeah, our control surface deflections. How are control surface deflections going to help us? I think everyone will agree that the main contributor is this rudder, right? You deflect the rudder, you get a lot of control in the yaw. Again, according to our sign convention, a positive rudder gives a positive yaw, right? Looking at this picture. So really, what I would expect here is that you take any of these curves. Let's maybe look at the alpha equals 0. Look at our nominal case. You kick over the rudder. All that's going to do is really shift this curve up, right? So now I'm going to draw this one parallel to the black line. So this one is your positive delta rudder, right? Because that will probably help you, with the yawing motion, right? Okay, so I think that's it. Okay, so at this point, tell you what, give me a second to erase the board, and I want to talk about where we are now. All right, so at this point, I think we've looked over and have a reasonable understanding of what we can expect to get from the wind tunnel in terms of your aerodynamic forces and your aerodynamic moments. So really, what we ended up getting and what we want to do is our wind tunnel is giving us basically CL, CD, CY, right? Those were our forces, and then CM let's call it the CG. Right? Let's say that you've transferred the moments to the appropriate location. So you get pitching moment, you get rolling moment, and you get yawing moment about the CG, right? You get those things. And now we understand how these dependencies come out, what they look like, how they change with control surface, angle of attack, dynamic pressure, all that kind of stuff. Now, the question is, what do we want to do with this data now? And what we're gonna try, and again, I'm coming at this from a GNC simulation engineer kind of controls perspective. This data is super helpful, but the way I'm gonna roll this into a dynamic model of my aircraft is I need the aerodynamic forces, right, as a vector. And I need the aerodynamic moments about the center of gravity of the vehicle expressed as a vector, right? So I need a 3-element vector here, and I need a 3-element vector here. Okay? Now, let's think about this. We should be a little careful. We specifically said at the beginning of this discussion that all of the data that we presented, and usually what the wind tunnel is going to collect for you, is these are all going to be expressed in the wind axis, right? So all of these are wind axis data, right? So I want this or it's easy for me to express this in the wind axis, right? So let's think about this. How do I turn these into those? What does this transformation look like? So what we better do is actually, let's come over here and let's draw our body frame of the vehicle, I guess. let me think about how we want to draw this, okay? So let's go like this, right? So here's your X body, what's coming out the nose. So here it is over here. Here's X body frame. The Y body axis comes out this way, right? So it's coming out of the page like this, out the right wingtip. And the Z body comes straight down through the floor of the vehicle, right? So it goes into the page like such, okay? Now the wind tunnel, right? These are in a different frame or a different axis. They're in the wind axis, but they're generally aligned in the sense that what we can do is, I think everyone would agree that the force in the wind axis X direction, right? So that is in this direction, right? So the wind, maybe I should draw this in a different color, right? Maybe in red, right? So here's the, this is a positive CD wind, right? Is in that direction. So what I'm getting at is this term right here in this bracket, let me make this a little bit bigger just so we have a little bit more room to write. I think it's going to take a little bit. This is in almost the opposite direction of where we eventually want to be. So you can write this now as negative CD, all right? Then I got to normalize this up because I want this in an aerodynamic force, right? So this is now negative CD times Q times SW, right? Okay, so that's the x-axis, and now the y-axis, right, is coming out the right wingtip. So that's basically side force, right? And I think that aligns, right? Because we said a positive side force is in this direction, right? So this is like this is like a positive CY wind, right? So I can write this as positive CY times Q times SW, right? And then finally, let's look at what goes in the x-axis, or excuse me, the z-axis, right? The third component. So let's see, where is Z wind? So Z wind is actually straight down, right? That's like your lift, right? So, oops, sorry, I drew this wrong. This way, right? This is what a positive lift is going to look like, right? Where did I draw? Oh, sorry, I have this L in the wrong spot. I don't even know why I drew that L earlier. Okay, so this is like, right? So here's a positive CL wind, right? Looks like that, right? Which is actually kind of in the opposite direction. So this actually becomes negative CL times Q times SW, right? Okay, so would everyone agree this now is how you take the wind tunnel data in the wind axis, right, to get the aerodynamic force expressed in the wind axis, right? And similarly, we can do the exact same thing for the moments and well, hold on, not exact. This is where we could potentially get bitten. Okay, let's figure out the x-axis. Where's the rolling moment, right? So the rolling moment, CL, that is about this axis, right? Which is aligned, yeah, so I think we said positive, let's keep this in red, right? We said a positive CL, right, in the wind axis was basically, was right wingtip down, right? Which is aligned with, quote unquote, not exactly aligned, but it's in the general direction of the X body. So this term here, the first one in the wind, this is going to be what? Positive CL, right? That's the coefficient of rolling moment. Now, when we renormalize this, we got to be careful, right? This is Q times SW. Now, what reference length did the wind tunnel use to normalize your rolling moment? So if it's like the Kirsten wind tunnel or some other tunnel, maybe this is your span, right? Okay? Now, okay, what about the second element of this vector? That is going to be pitching moment, right? So pitching moment, where is your positive pitching moment, right? So we have positive pitch, maybe we could draw it over here, positive CM wind, right? This is approximately nose up, right? okay, which does align with the Y body. And again, I keep saying align. I really should stop using the word align because they absolutely don't align. The wind and the body axis do not align. That's what we're doing right now. So I'm using, whenever I say align, let me put this in air quotes, right? And we'll deal with handling these air quotes in a second, right? Because I am playing a little fast and loose. But okay, positive CM wind. So this should be positive CM for pitch. Now here we go. This is where you can get bit really easy, right? The reference length for a pitching moment, that might be different. This is C bar for some situations. Like your mean aerodynamic chord is how you would renormalize your pitching moment. That comes from the wind tunnel, right? Okay, and now our final last one, the third thing is about the Z-axis. So that's over here. So I think we said positive C yaw, right, in the wind was nose right. Let's assume that's what the wind tunnel returns to us, right? Is a positive nose, or CN tends to push the nose right, which again tends to be, again, quote unquote, aligned with the Z body. So I think that should be also positive. So we end up with a positive CN times Q times SW times B ref, right? Would everyone agree? Great. So at this point, check this out. We have the aerodynamic forces expressed in the wind frame, the aerodynamic moments about, you know, I put CG here, right? But this is really, as you understand, any model moment center, right? Of where the wind tunnel decided to give you the data. You got to make sure you transfer this to the right location. Hopefully the model moment center is the center of gravity of where you want to go, right? And here, again, I'm just going to call this out again. Don't screw this up, right? Some of these, just make sure you're consistent. Whatever the wind tunnel gave you, right? Make sure you renormalize it using the way they normalize the coefficient data, right? This has units of, you know, inch pounds and Newton meters, what have you. This is a proper vector that you can draw in space, right? This is the aerodynamic moment vector on board the aircraft. And again, one other thing that I'll maybe throw in here, I did put aerodynamic here. But if you had a powered model, you got to be a little careful because the powered model now throws some thrust propulsion effects, and sometimes depending on how you model this, you might want aerodynamic and propulsion data completely separately. Again, that comes up to you as a simulation engineer when you put this thing together in a dynamic simulation. You just don't want to be double counting things. So mostly, you know, maybe this is a good time to say, you know, it's very rare that you'll see a powered wind tunnel model. Mostly when you go to the wind tunnel, you want just aerodynamic effects. So you won't have an engine on your model, right? You might just have an empty non-functional engine just to get the aerodynamics right, but you won't actually have the engine to be able to spin up the throttle and all that kind of stuff. But anyway, long story short, here you go. Now, what we can finally do with this, right, is you basically have this in the wind frame. You can now rotate it to the body frame if you want. So that was why I kept saying this quote unquote. Let's take care of this quote, this air quotes, right? To get the aerodynamic forces expressed in the body frame, well, now we have the aerodynamic forces expressed in the wind frame. All I need to do is rotate this, oops, sorry, this is wind frame, rotate it from the wind frame to the body frame. And we know that this is now, again, a two-angle rotation over the angle of attack and the angle of side slip, if you watch our previous video on stability frame, body frame, wind frame, all that kind of stuff. So here you go, and same thing, I need the aerodynamic moments about the center of gravity expressed in the body frame. I have the aerodynamic moments about the center of gravity expressed in the wind frame. So just rotate this from the wind to the body frame. So here you go. We finally end up with, this is what we went to the wind tunnel for, right? We went to the wind tunnel to get all of this information. Here we go. So yeah, you spend a couple $1,000s, several weeks in the tunnel to get all this data, but now you have a great understanding of what do the aerodynamic forces look like in the body frame, and what do the aerodynamic moments about the center of gravity look like in the body frame. So this is what you spent all that time, money, and effort on getting, right? So okay, before we leave it, I think what I want to do now is, okay, that's what we're doing. We talked about the data acquisition, we talked about the data reduction, we talked about the data analysis portion of it. Before we end the video, let's talk about some considerations that if you're planning this wind tunnel test, right, if you're spending all this time, money, and effort to get to this, there's a lot of potential pitfalls or holes you can fall into. Let's think about what are some of the considerations that need to be taken into account in order to conduct a successful wind tunnel experiment. All right, so the first set of considerations you might want to think about during your wind tunnel test centers around constructing the model. So if you're building the model, or probably more likely having the model built for you, what might you want to do or think about? So in no particular order, I thought we maybe would list some of these things that you might want to keep on your radar. So for example, do you want to make sure that the model is able to be inverted as well as accommodate an image strut or an image fairing setup? So again, if you do this, it'll allow you the ability to make some of these Terran interference effects that we talked about in our previous video. Kind of in a similar fashion, while centered around these corrections, we saw that in some situations, particularly for the wall corrections, you might need to be able to have a completely removable horizontal stabilizer that will allow you to isolate the CL of just the wing and therefore apply wall corrections. Similarly, wall corrections also needed to see that and experimentally measure that parameter of how the pitching moment changes with the change in stabilizer angle. So not only do you need the removable tail to be completely removable, but you need this tail to be able to move to different incidence angles so that you can experimentally measure DCM DDS, kind of like we just talked about on the board. How about control surfaces, right? So the previous bullet dealt with changing the incidence angle of the entire horizontal stabilizer. Well, what about the individual control surfaces like the ailerons or the elevators or the rudders or the flaps or any of these things that we just talked about, and we looked at how those control surface deflections will definitely have an influence on some of the force and moment data that you collect in the wind tunnel. So you may want to have your wind tunnel model have the ability to deflect these control surfaces. So oftentimes these will literally be different control surfaces or different parts of the model that you screw on and then remove and then add a new piece on and screw that new piece on. So it takes a little bit of time to bring the wind down and do a model change, bring the wind up, collect another set of data. So in the recent past, motorized model changes have become more and more popular. So if you have the time and money and sophistication, you may want to build a wind tunnel model with actually have things like servos, and actuators inside it so that the control surfaces can be deflected and you can move to a different testing condition without ever having to bring down the wind. What else might you want to think about? How about an accelerometer? So for measuring angle of attack, oftentimes what's done at wind tunnels is an accelerometer will be added and installed internally to the model. So if you want to do that, you're going to need to be able to obviously have an empty space in there to store that accelerometer. So you're going to have to build that in before you even walk into the wind tunnel. While we're talking about building things into the model, how about power testing? Like we just saw, having a powered actual propeller or an engine or some kind of propulsion mechanism can influence the flow field and influence the aerodynamic force and moment data that you collect in the tunnel. So do you want a model which actually has a spinning propeller so you're able to conduct this type of power testing? While we're talking about non-standard testing, how about pressure ports, right? If you remember back in our first video, we talked about pressure taps or pressure ports in order to collect extra data about aerodynamic performance in the wind tunnel. So if you want to do that, again, this is not something you can decide to do during the wind tunnel test. You have to plan for this ahead of time by adding pressure ports all over the surface of the model, as well as the internal tubing to route that pressure data to a EPS module. So long story short, these are just some of the things. It's by no means an exhaustive list of some of the things that you're going to need to think about when you are having your wind tunnel model built. All right, so you've got your model built, and now we're in the tunnel actually conducting our test. There's a lot of things you're going to need to think about while you're actually conducting that test. So again, in no real particular order, let's just start talking about some things you might want to consider. So for example, what kind of ranges of angle of attack, angle of side slip, dynamic pressure, etc., which of these independent variables do you actually want to test at, right? You want to make sure that you're covering the appropriate flight envelope, right? So if this is a cruise kind of commercial airliner situation, you don't need to be collecting alpha data at -45 to +45 degrees angle of attack, right? Because the aircraft is never going to be operating in that regime, so you don't want to be wasting time. Also, while we were talking talking about that sort of CL versus alpha curve and kind of stall, and we said that, you know, you may want to think about for your alpha runs that you're doing, sometimes referred to as alpha flags, that will define which angles of attack you want to stop and take data at. You might not need that to be a linearly spaced set of points, right? Because a lot of the data is kind of boring in that linear region. You might want to take coarse steps and then take finer data points near stall and collect data where you actually care about. What else? Oh, how about which configurations are critical to obtain lift sets and strut and interference tears for? So remember, the idea with the lift sets were you needed to isolate the lift of just the wing so that you could apply wall corrections. And in order to do that, you needed to take off the tail of the model and do a run. So again, you don't want to be getting lift sets for absolutely every single blinking configuration because that's just going to take too much time. So there might be some critical configurations that really matter, and maybe those are the ones that you actually obtain full-on lift sets as well as maybe inverted plus image fairing runs so that you can apply tear and interference for some of these cases that you really care about. You know, things like maybe nominal cruise conditions or something like that where the airplane is going to spend a ton of time there, so you really want to get the right answer at those configurations, but you don't really care about it for some of these other situations. Along a similar vein is you might want to think about as you're conducting the wind tunnel test, right? If you make a model change, a significant model change, like you add on a whole new horizontal stabilizer, a different configuration where this different part on the model might be significant enough to change the center of gravity of the model, right? And we saw earlier in our data reduction discussion that if you change the CG of the model, you're going to have different weight tears that need to be taken into account, right? You're going to have a weight tear due to pitch and a weight tear for a roll. So again, you don't need to conduct a brand new weight tear for every single configuration change, right? If you deflect the aileron angle just a little bit, right, you make a model change to just change the aileron deflection, that's probably not going to change the CG of the model in a significant enough way to warrant a new weight tear. So again, as a test engineer or the test director, you need to be thinking about this of which configurations do I actually need to stop and take the time to either do that full table tear or that 3-point weight tear. While we're talking about spending extra time and money, how about that whole discussion on flow visualization, right? Flow visualization is helpful and generates a lot of pretty pictures, but it actually probably won't get you aerodynamic data at the same time. Why, you ask? Well, we saw all those different flow visualization techniques. Some of them can be kind of messy, right? So some of them, like China clay or oil, you may need to actually tape off the balance and or pressure ports on your model. So in other words, you're going to have to cover up the pressure port so you're not going to be getting any pressure data. You can't afford to have that gunk of China clay run its way down the strut and into the balance. So you're going to have to tape off the balance, therefore fouling it, therefore invalidating any force and moment data you collect on these runs. So if you want to do some of those messy flow visualization techniques, you're going to have to sacrifice and do a aerodynamic data run followed by a flow visualization run, and maybe followed by is the wrong way to state that, because we'll talk a little bit later about intelligently staggering your runs. But long story short, you're probably going to have to do 2 runs in order to get that data. So flow visualization is, again, something you might need to think about. Now, as we saw earlier in the flow visualization, there are many different types. So other things like maybe smoke or mini tufts might be a good way to kill 2 birds with 1 stone, in the sense that you can probably collect aerodynamic force and moment data at the same time as collecting flow visualization data, because those techniques are relatively clean and don't require you to tape up the model or the balance. Let's keep going. What else, while you're conducting this wind tunnel test, do you have to think about? Well, what if you have a non-standard model, right? Which of the corrections are actually needed, right? Remember our previous discussion where we spent almost 3 hours talking about all the different ways you can apply corrections to the data. Well, some of these probably don't make any sense if you have a non-standard model. So for example, if you don't have an aircraft, what if you had like a car or something like that that's normally on the ground? That opens up a whole nother ball of wax, but long story short, some of these things might not be appropriate any longer. For example, like wall corrections, right? So some of these things, if you have wall corrections, or maybe you're doing other situations like an aircraft, but all you care about is takeoff and landing data. Well, if that's the case, then you don't need to apply wall corrections. Therefore, you don't need to get wall lift sets. Therefore, you don't need to calculate DCM DDS. So you can actually save a bunch of time if you don't want some of these corrections. So again, as a test engineer, you need to step back and think, what do I really care about, and what can I cut in order to save time and money, right? While we're talking about saving time and money, right, you may want to think about ordering your runs so that you can minimize the number of model changes, sometimes known as DFMCs, or downform model change. And the reason it's stated that way is, you know, if you have a set of changes or model parameters that need to be swapped that require you to bring the wind down, it can take a few minutes to bring the wind down, to open the doors, to get in and conduct the model change, to bring the wind back up onto condition, and then start taking data again. So long story short, you could have 10, 15, 20, 30 minutes between of just downtime where you're not collecting any aerodynamic data, and that was a consequence of you needing to make some kind of model change. So you don't want to be stacking up DFMCs one after the other. You want to try to keep gathering as much data as possible before you come down and collect wind tunnel, or before you make that model change, right? So you want to collect as much data as you possibly can. And the reason why is just purely economics and time, right? For example, at the Kirsten Wind Tunnel, I think the last time I checked, it cost $650 an hour to test there. So if you're talking about burning 30 minutes for a model change, right, that's a non-trivial amount of money that your project or your program is going to have to pay for. Other more specialized wind tunnels, like the Onera F1, which is a pressurized wind tunnel, that can be $40,000 a day to test, right? So now coming down for a model change is suddenly a really big deal. So you need to be planning these runs so that you get as much data before coming down for a model change as possible. What else? Oh, how about calibration? So periodically through the day, you might want to recalibrate the balance or re-zero your pressure system. How often do you want to do that? Again, you don't want to be doing this after every single run because that's going to cost you time and money. So do you maybe do it once a day, twice a day, etc.? Do you do it when the temperature or the ambient pressures change? Again, it's up to you as a test engineer to decide this and document it, and just balance engineering accuracy versus time and money, all right? You know, and lastly, one of the things that you really want to think about, even maybe before you get into a wind tunnel, is you should ask yourself, does the wind tunnel that you're interested in support the flight envelope that you desire? You know, for example, can you actually jam can the model scale be appropriate? You know, is the tunnel big enough so that you can get a reasonably sized model in there to obtain the proper Reynolds or Mach number effects, right? And if it doesn't, do you need a specialized facility like a full scale wind tunnel, or even some of these tunnels like we mentioned earlier, like this Onera F1 tunnel, which is actually pressurized so that you can manipulate both Reynolds number and Mach number sort of independently. So there's a lot of interesting questions here that you might need to ask, and actually a lot of these engineering questions drive the design and the construction of some other specialized wind tunnels, like we saw here and mentioned, like the Onera F1, like the kinetic wind tunnel, and things like the NASA icing research tunnel and things like that. So again, this is a not exhaustive list of some things you might want to think about if you're the test engineer and you're in charge of running a wind tunnel test.
All right, so there you have it. Those are some of the things you might want to think about if you want to go ahead and conduct a wind tunnel test. So with that being said, I think this is going to close out our three-part series on wind tunnel data acquisition, data reduction, and data analysis. So hopefully this crash course has given you a little bit of feel of what wind tunnel testing is and how you can leverage that to basically obtain aerodynamic information about your aircraft, which you can now take some next steps. In fact, we'll do that in our very next video. Is where do I take this information, right? I got all of this. I need to now jam this into an aircraft model or a dynamic simulation, or basically do some further engineering analysis to help me further my aircraft design and production. So with that being said, I think this is probably a good spot to leave this video. I hope you enjoyed it, and if so, I also hope you'll consider subscribing to the channel. If you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. And remember, the new videos come out every Monday. I try to be fairly regular with those, and I hope that I'll catch you at one of these future discussions and we can all learn something new together. So until then, I think I'm going to sign off. Talk to you later. Bye.